class. In this video we're going to be talking about applications of linear equations. So in our last video we talked about linear equations kind of in this general sense. Those were those equations, so two things that are equal, that only have powers of x to the first. Remember, we had that one that was in disguise that actually had an x squared in it, but we have linear equations in one variable that only have a power of 1. And so there's kind of a six-step process for solving application problems. And then this is actually on page 92 of your textbook, and so I really recommend that you check that out because they have a lot more words than I'm going to write here, together with a couple examples that follow it where they say step 1 we do this, step 2 we do this, step 3, and so on, right? And so step 1, identify the quantity the variable should represent. So before we can even start to solve an application problem, we need to figure out what is unknown. What is the quantity that our variable should represent? And while I'm just going to give you the 6 steps now, I'm going to work through a number of examples where we apply these steps in order, and we kind of see, depending on what the question asks, sometimes we can stop at, say, step 3, step 2, sometimes we have to go all the way to step 6. So identify the quantity the variable should represent, and then we're going to do what's called declare a variable to represent that quantity, and we're going to express any other unknown quantities in terms of that variable. And then after we do that, we're going to write an equation, right? Because at the end of the day, we're looking at linear equations. Write an equation that relates those unknown quantities. Then we're going to solve the equation. We're going to then make sure that we answer the question that's asked. In that problem. And then we're going to check the answer in the original. So our 6-step process for solving application problems. You're going to first identify what we should represent with a variable, and then we're, declare a variable to represent that unknown. We're going to write an equation, solve it, make sure we answer the question that's asked, and then we're going to check our answer. And so these are the steps we're going to talk about, or we're going to use in the next several examples. And now, because application problems tend to be really about like word problems and making sense of the context, I'm going to go ahead and use a PDF of these problems instead of writing them all by hand. But I am going to keep my 6 steps nearby. Maybe actually when I need to, I'll bring this little 6-step one in. So identify, declare, write an equation, solve, and answer, and check. So here it says Desmond buys inline skates for $327.62, and that is with sales tax. And we know that sales tax is 6.5%. And I would say rarely do we actually work with percents like that, so let's go ahead and convert it to a decimal. 0.065, 6.5% tax. And it says let X be the price of inline skates before tax. So here it already says, so if we look at our 6-step process, identify the quantity the variable should represent. Well, it already went to step 2 and declared our variable. So this is step 2. Let me get a different color so it'll pop. So we're starting right at step 2. It says write an algebraic expression in X for the tax paid on the inline skates. So X is our price, and if we need to find the price or the tax on that, we need 6.5% of that, so 0.065 times X. And so that is, in essence, the second part of step 2. So I'll go back to this. It says, so declare your variable and then express other unknowns in terms of that variable. So we don't know what the amount he paid in tax. So this is unknown. So the amount paid in tax is unknown. But we could represent that in terms of our variable, the price of the inline skates, directly. And so it said write an algebraic expression. That looks like an expression to me. We're good to go. And so another example. That's why I said sometimes, depending on what the question asks, you can stop at, say, step 2 or step 3. Now we have number 12. It says an air conditioning repair bill for $229.50. So our total bill was $229.50. It says it showed a charge of $72 for parts, so we know that $72 for parts, and the rest was labor. It says let X be the number of hours of labor it took to repair. So let X be number of hours of the repair. Write an algebraic expression in X for the labor charge per hour. Labor charge per hour. We don't know. And so again, it did the step of declaring our variable. So we're in step 2 already. And what we're doing is we're writing this other unknown, labor charge per hour, in terms of X. Well, if $229 was our total bill, and the parts were $72, and the rest is labor, how much was labor? So the labor cost is going to be $229.50 minus 72, and whatever that comes out to. And so that was the total labor cost. And we know that it took X hours. And so if that's the total, how do I find out how much it was per 1 hour? Well, labor charge per hour is total labor cost over the number of labor hours. And that means we take this 229.50, ignore that decimal, minus 72, and we divide it by the total number of hours, X. So that means if our number of hours were, say, 2, let me go ahead and I'll get us a real number, 229.50 minus 72. It gives us 157.50 over x. And now suppose that we did that in 2 hours. 2 hours, or the repair was 2 hours, that means they paid $78.75 an hour. That's probably a little high. So let's say instead of 2 hours, they did it in 3. 3 hours would mean that it was $52.50 an hour. That's probably a little bit more reasonable. If instead of 3 hours, that was really 4 hours of labor, it means it was only 39 and some weird fraction, $39.38 per hour. And so that one's probably most believable, but again, all it asked was write an algebraic expression in x for the labor charge per hour, which means that this is your answer. But I just wanted to illustrate kind of what you could do with that equation or expression once you had it. So the biggest part about writing these sorts of expressions is figuring out how we relate the things that we don't know to our already declared variable. So I'm going to work with one more example on writing expressions. And so we're going to dwell just in step 2 for a little bit, and then we're going to bring them all together in a few more examples. So, number 16. Number 16 says that dried pears sell for $5.50 per pound and dried apricots sell for $6.25 per pound. So let's write that. Pears, $5.50 per pound. And then it says apricots are $6.25 per pound. Let x be the number of pounds of dried pears. So we're already in step 2. Let x equal number of pounds of dried pears in a 15-pound mixture of pears and apricots. And it wants 3 algebraic expressions. The number of pounds of dried apricots in the 15-pound mixture. Well, apricots is equal to, well, what do we know the total amount is? We know the total is 15 pounds. And we know that x is the pounds of pears. So it's going to be whatever in the 15 pounds isn't pears. 15 minus x. So suppose there were 2 pounds of pears, there'd be 13 pounds of apricots. Or if there were 8 pounds of pears, 7 pounds of apricots, right? So it's whatever is left. And then it says, write the value of the apricots in the mixture. Well, so value is just going to be price times amount. And it gave us at the beginning that the dried apricots were worth $6.25 a pound. So $6.25 per pound. Times, and how many pounds of apricots we have? Well, we have 15 minus x. So you could write it this way. 6.25, 15 minus x. And then the last thing it wants is the value of dried pears. So value of pears is going to be price times amount. Gave us at the beginning that pears were worth $5.50 times the amount. X is the number of pounds of dried fruit, so 550 x. That was going to be multiplies, and then I just like, make it an x. Okay, so again, we started in step 2. where we had a variable already declared and we were writing unknown in terms of our variable. Because sometimes that'll turn out to be the hardest part of a problem. Other times it'll be hard to decide what your variable is. Other times it'll be hard to solve it. And so now that we've spent a little bit of time in step 2, we're going to look at all of the steps together. But I really think that this was worth kind of this practice of, well, if we know one thing, how do we get to other things? So, number 22, test scores. So it says Jocelyn's first 3 test scores are 85, 76, and 88. If the final exam counts as 2 tests, what must Jocelyn score on the final exam to raise her average to 85? Well, step 1, I'm going to use 2 colors. Step 1. What should our variable represent? Well, it's what should she score on the final exam? So let X be Jocelyn score on the final. And I guess that was actually more part of step 2. Declare it, and then write an expression relating the unknowns. Well, if we want to find the average, we add everything up and we divide it by the total number. So we have, so step 3 is we're going to do our unknowns. Well, there are no other unknowns. We just need to know what X is. So there are no other unknowns. And then when we get to step 3, write an equation that relates the unknown quantities. Well, we know that she gets an 85 on her first, a 76 on her second, and an 88 on her third. It says the final exam counts as 2 tests, so let's just go ahead and add that score twice. Which means we're really finding the average of 1, 2, 3, 4, 5 single exam weighted things. And Jocelyn wants her average to be an 85. So this is our equation. We have 85 plus 76 plus 88, plus we have to count and weight this final exam as 2 exams. So we divide by 5, and that gives us 85. Step 4 then is solve. You can multiply both sides by 5. So we get 85 plus 76 plus 88 plus 2x. So simplify that. Multiply both sides by 5. We're going to get 8 times 5 is 400 plus 25, 425. And then, because we have calculators are friends, 425 minus 85 minus 76 minus 88. We get 176. 2x equals 176. So here I just added those up and subtracted it. And just to give you an idea, 85 plus 76 plus 88 is 249 minus 249. Double check my math always, 176. And then we divide by 2, x is equal to 88. So step 4 says solve. Step 5 says answer the question that's asked in the problem. The question asks, what must Jocelyn score on the final exam to raise her average to 85? The question doesn't say what is x, so we say Jocelyn must score 88. And then step 6, where we check our answer, we can go back to the original. So it should be the case that 85 plus 76 plus 88 plus 88 plus 88 divided by 5 should give us what we wanted. So we have 3/88, 76, and then 85. Divide that by 5, and we do, in fact, get 85. Good. So we've looked, those first couple examples, we were living just in step 2 at other unknowns. And now we're bringing all of these pieces together of, so declare a variable. If there are other unknowns, relate them. Here there weren't. Write an equation. That means there should be an equal sign. Solve that equation. Step 5 says we need to reinterpret that solution in the context of the original equation. Jocelyn has to score an 88 on the final. And then we should always check our work. We took the average of those 5, and we did get 85. And so this is an example where this 6-step process will always work when you're working on a problem. It'll always give you a way to figure out what we don't know, relate that to the other unknowns if necessary, set up an equation, solve it, interpret, and check your answer. And unfortunately, that's as good as we can do when it comes to problem solving, because there isn't going to be a single formula or a single thing that always works. The best we have is a process. So moving to another example. This one's a little bit longer. So it says engineering degrees. So if anyone has engineering in their future, we'll talk about that at the end of this problem. It says among a group of engineers who had received master's degree, the annual salary S in dollars was related to two numbers B and A. So they said, well, S is salary. B was the number of years of work experience before the master's degree. So B is number of years before master's. And then A is the number of years of work experience after the master's. So A is number of years after master's. The relationship between S, A, and B, and so that's our step 2. So again, they're going to put us in at step 2. We're going to express other unknowns in terms of the variable. It says that S is related to A and B as 48,917 plus 1080B plus 1604A. It says if an engineer had worked 8 years before earning her master's degree, so just kind of some notes. So worked 8 years before, B being number of years before, so B equals 8, and was currently earning $67,181. How many years did she work after receiving her degree? So how many years after? That means A is what? So let's go ahead and go to our equation that relates the unknown quantities. So that's step 2. That's sort of step 3, but let's go ahead and write step 3 here. Salary is known. She's earning $67,181. That's equal to 48,917 times 1080 number of years before plus 1080, and B is 8 plus 1604. A is our unknown. And so this is our equation that relates all of our known to our unknown. And now it says to go ahead and solve this equation. So we have, let's go ahead and we'll simplify this right hand side first. So 1080 times 8 gives us 48917 plus 8640 plus 1604A, 7181. And now I'm just going to go ahead and subtract both of these over. 48917 minus 8640, so minus 48917 minus 8640. Those will cancel. Let's go ahead and put this in. $67,181 minus $48,917 minus $8,640. I typed it wrong because I got a negative number. 67181 minus 48917 minus 8640. 9,624 equals 1604A. Divide both sides by 1,604. We get A is equal to 6. So the question said, how many years did she work after receiving her degree? Well, A equals 6 doesn't answer that, but, so that was step 4, solve. Step 5, she worked 6 years. And then it says, check your answer in the original. So that's where we want to take 6 and substitute it up here for A, and our 8 for B. And if we do that, we end up with 48. Oh, that's here. 1080 times 8 is 8640 plus 1604 times 6. And then we add to that 48917, and we get 67,181. So we didn't make a mistake. Perfect. Now my comment about that is, if an engineer with 8 years of bachelor's working experience and 6 years of master's working experience is only making 67,181, they're being underpaid, and they need to negotiate a raise. All right. We have our last example for today. For our last example, we're going to be looking at plowing a field. It says a farmer can plow his field by himself in 15 days. If his son helps, they can do it in 6 days. How long would it take his son to plow the field by himself? So if we start with step 1, what is our unknown? The quantity to the variable should represent. So let's say that's the rate the son can plow. And then step 2, it says declare a variable to represent that. So let x be the rate, or maybe instead of rate, the fraction of the field the son can plow in 1 day. And then step 3 is writing an equation that relates all of our unknown quantities. Well, let's get down what we know before we write down what we unknow. So we know the farmer plows the whole field in 15 days. That means the farmer plows 1/15 in 1 day. We know that the farmer and sun plow whole field in 6 days. Or the farmer and son together plow 1/6 in 1 day. And so we know that the farmer plows a 15th plus however much the son can plow in 1 day has to be 1/6 of the entire field each day. And so that is step 3. Step 4 is to solve the equation. Here we have x equals 1/6 minus 1/15. Our common denominator, we have a 2, a 3, a 3, and a 5. 2 times 3 times 5 is 30. So we get 1, not 1. So what do we multiply 6 by to get 30? Multiply it by 5. Minus, what do we multiply 15 by to get 30? Let me move that up. 2. Which means we get 3 over 30, or 1 over 10. And then our step 5 says answer the question. So it says, so this tells us that the son plows 1/10 of the field per day. Step 5, answer the question that's asked in the problem. It says, how long would it take his son to plow the field by himself? Well, if he can plow 1/10 in 1 day, it'll take him 10 days. The son will take 10 days. Step 6 says check the answer in the original. Well, so we have 1/5 plus 1/10, and that should give us 1/6, and it does. But we can also look at the original question on the screen above me. It says, if the father can do it in 15, and the son can do it in 10, together they can do it in 6. And it's like, yeah, that's probably, that seems reasonable. Sometimes checking an answer in the original just says, does this answer make sense in the context of the original? So suppose the farmer could do it in 15, and we got that the son could do it in 30. Would we expect them to be faster? No, because if the son could, I mean, maybe a teensy bit faster, like maybe 14 days. But we certainly wouldn't expect them to get it done in over half the time, or in under half the time. And so sometimes checking the answer in the original is a matter of making sense of it. Does this make sense in this context? Another example might be like in the tax problem, if we said that $100 of that was tax, that would be closer to 50%, right? And so there are these sort of checks that we can do to make sure that they make sense in the context. But that's where we'll end for today. So really, problem solving is about practicing. What is the variable? What don't we know? How can we relate what we don't know to the things that we do know? When we do that, what equation relates those to each other? Then going through the process of solving that equation, and then converting that answer back to the context of the problem. So what is the question that was asked, and what is its answer? And then checking it either by resubstituting it into an equation and making sure the math double checks, or making sure that it just makes sense in the context of the problem. But there will be a number of these for you to practice. I would highly recommend, if this is one that feels a little bit rougher, to look at the section. So starting on page 92 with the 6 steps, there are several examples that step through this process. And in the homework and in the odd problems that follow it are really great practice. But have a great day, everyone.